So good evening, everyone. I am Calvin Joseph, and today I'm going to conduct the Week 5 Problem Solving and Doubt Clearing session for the course State Space Approach to Control System Analysis and Design, which was taught by Professor A.P. Tiwari. Okay, so today I'll be teaching regarding certain mathematical preliminaries, which Sir has also taught about positive definite. When do we say a function is positive definite, negative definite? Positive semi-definite, negative semi-definite, how do we say a matrix, what is a quadratic form, etc. We will be touching about those. Then also I'll be teaching about what is stability, like finding the stability of a system is very important. Like the system has to be stable, then only we can use it and we can operate it. Like all the systems, we have to check whether the system is stable or not. Okay, and one of the methods which we can use to check stability is Lyapunov stability. Right? So these are things which we'll be considering today. And then in the mathematical preliminaries, I'll be touching upon what is the definiteness of a scalar function, what are quadratic forms, what is the definiteness of a quadratic form, and what is a simple closed surface. So all these mathematical concepts are required such that we can understand what is Lyapunov stability and how do we use these mathematical concepts to, to determine the stability using the Lyapunov principles. Okay, so let's get started. So week 5, I've started with the mathematical preliminaries. So let us consider a function f of x. Okay, it is given by x square, right? So at f of 0, it is 0, and f of x is not equal to 0 when x is not equal to 0. Okay, and another thing is f of x is greater than 0 when x is not equal to 0. So such a function is known as a positive definite function. So what does it mean is that we can guarantee that this function value will always be positive, okay? And it is 0 only at the origin, only when x is equal to 0, right? Suppose we made it f of x is equal to minus x raised to 4. Okay, let us make it minus x raised to 4. For this, what do we know? Again, we know f of 0 is equal to 0. And f of x is not equal to 0 when x is not equal to 0. But f of x is less than 0 when x is not equal to 0. So this function is a negative definite function. Okay. We can be sure that it will always be negative. Suppose our function f of x was, let us say, x squared minus x raised to 4. Okay, so this would be what? It would be x squared into 1 minus x squared, right? So in this case, there are two conditions. It is 0 at f of 0 is equal to 0. This is true. But f of x can be less than 0 and f of x can be greater than 0. Both cases are possible. So that is why we say that this function is indefinite. It is an indefinite function. Okay. So I have some questions. Let us look into the question. So let us consider this case. So we have to state the definiteness of the below scalar function. So we already touched it for the case f of x equal to x square. Let us consider the case when f of x equal to x cube. Okay. So question 1, we have to see for f of x equal to x cube. Okay. So let us start. Simple way. Let us have a table. This is x and this is f of x. Okay. If my value of x is 0, what is my f of x? My f of x is 0. If my value of x is 1, the value of f of x will be 1. 1 cube is 1. The value of x is 2. F of x is equal to 8. All right. This is the values of this. But if we make x to be minus 1, then f of x comes out to be minus 1. If we make x to be minus 2, then its value comes out to be minus 8. Okay, so if we plot it, right, this is our x of x, this is f of x. Let's say this 0, 1, 2. This is say 1, this is say 8. This point is minus 1, this point is minus 8. This is minus 1, minus 2. So it goes through these points. Okay. So this color, this point, this point, this point, this point. So the curve actually will go like this. So, so this is the plot of f of x. So now if you consider, is f of x positive definite or negative definite or semi or indefinite? So if you will look at this, f of x is taking value less than 0 and f of x is taking a value greater than 0. So we can say that f of x is indefinite. Okay, we can say f of x is indefinite. But there is a condition when f of x can be told to be positive definite. If we say that my x, range of x, is between 0 to plus infinity. If it is between 0 to plus infinity, then what can we say? We can say f of x is always greater than 0 in this range. So in this range, my f of x is positive definite. Okay. And if we say when x is less than 0, that means it goes from minus infinity to x to 0. Then we have f of x is less than 0. That means f of x is negative definite. Okay. That means f of x is negative definite. All right. So that's why for x cube, we could say that it is indefinite. But if there is a certain range, then we can say that it is positive definite or negative definite. All right. So let us go to the next question. So find the definiteness of the below functions. Okay. So first function is f of x equal to 2x1 square plus x2. So this is question 2. A part, f of x is equal to 2x1 square, 2x1 square plus x2. So here x is a vector which belongs to, it's a 2 row. So x has two components, x1 and x2. Okay, there's two components, x1 and x2. So f of x equal to 2x1 square plus x2. So what can we say? Can f of x be negative or is it only positive or it is always only negative? Okay. So let us consider a case. Let us say x1 comma x2. Oh, it would be better if it's in a tabular format. We have x1, we have x2, we have f of x. Right? I put both as 0. Then my f of x comes out to be 0. If I put x1 as 1 and x2 as 0, f of x comes out to be 2. If I put x1 as 0, x2 as 1, f of x comes out to be 1. Okay, here all it is fine. And if you will look at it, you can understand that if you put x1, x2 to be positive, f of x is always positive. Okay. But now let us put x1 as -1, x2 as 0. You will get f of x to be 2, which is again positive. But if you put it as 0 and -1, you will get f of x to be -1. So there is a case when f of x is less than 0. So then we can conclude that f of x is indefinite. Okay, it is an indefinite function. And how do we know that? Because uh, if you will observe, there's plus x2. So x2 can take positive value or it can take negative value. And there can be a case when 2x1 square is 0. So that is why we say that f of x is indefinite. Right. Okay, so let us go to the B part where f of x is equal to 2x1 square plus x2 square. Okay, f of x is equal to 2x1 square plus x2 square. Now, how will we analyze this? So, if x1 is positive or negative, so this is x1, this is x2, this is a f of x, right? So I put x1 0 0, this comes out to be 0. x1 is 1, x2 is 0, this comes out to be 2. x1 is 0, x2 is 1, it comes out to be 1. Let me put x1 as -1 0, this comes out to be 2. If I put this as 0 and -1, this comes out to be 1. Okay, so if you will plot this function 2x1 square plus x2 square, if x1 is negative, x2 is negative, still their squares will always be positive. And you add positive and positive, it is always positive. So f of x is always greater than 0. That is why we can say that f of x is positive definite. Okay, f of x is positive definite. But this is for the case when x belongs to R2. Okay, x is belonging to R2. What will we say for the case that f of x is which is this third part, f of x equal to 2x1 square plus x2 square, and x belongs to R3. Okay, so f of x is equal to 2x1 square plus x2 square, but x in this case belongs to R3. So f of x actually is what? 2x1 square, okay, 2x1 square plus x2 square plus 0 into x3 square. Okay, so this is my f of x, right? So what do we know? Like in the previous case, my f of x was 2x1 square plus x2 square. And f of x is always greater than 0, except for the case where f of 0. That is, in this case, f of 0 is 0. But for any other case, f of x is greater than 0 in this case. Okay, but when we will go to this scenario, when x is in three-dimensional plane, so it is 2x1 square plus x2 square plus 0 into x3 square. Okay, so let us do, this is x1, this is x2, this is x3, and this is f of x. All right. So if I put this is 0, 1, 0, what will I get? I'll get this one, 1, 0, 0. I will get this to be 2. If I put the 0, 0, 1, I will get it to be 0. So if you will look at this case, okay, we will look at this case. In this case, you will notice your x is not equal to 0. What is your x? Your x actually is over here is 0, 0, 1. Okay, so x is not equal to 0. But your f of 0 means, your f of x has come out to be 0. So that means this is a positive semi-definite function. Positive semi-definite function. Okay, so there are, when x is not equal to 0, there are some cases when f of x is equal to 0. Okay, so that is why it is a positive semi-definite function. And f of x in other cases is greater than 0. It is never negative. Okay, so that's why it is positive semi-definite function. Okay, so proceed to the next question. Okay. Write the quadratic expression in quadratic matrix form and determine its definiteness. All right. So, question 3. So, this is my f of x. F of x is equal to 2x1 square plus x2 square, 2x1 square plus x2 square plus 5x3 square. Okay. This is my f of x. Now I have to write it in a quadratic form using matrices, right? So as sir taught, we write it as f of x is equal to x transpose r x. Okay. So you must understand that x is a row, it is a column vector. Okay, r3 cross 1. So x actually is x1, x2, x3. All right. And your R matrix is a 3 row, 3 column matrix which has R11, R12, R13. This is R22, R33. These are the diagonal elements, and all diagonal elements are symmetric. So if this is R12, this also will be R12. This is R13, this will be R13. Let us say this is R23, so this will be R23. Okay, so this is the matrix. So now what is X transpose Rx? So X transpose Rx actually is equal to, this is what, x1, x2, x3 into R11, R12, R13, R12, R22, R23, R13, R23, R33 into this x1, x2, x3. Okay. Um, so if you will multiply throughout, okay, if you will multiply it throughout, you will get it in the form of x1. It would be r11 into x1 square plus r12, 2 times r12 into x1 into x2 plus 2 times r13 into x1 into x3 plus r22 into x2 square plus 2 times r23 into x2 into x3 plus r33 into x3 square. So this is the generalized expression. Okay. So now we will compare this. This we will compare with this. Okay. So we will compare them. What we will get, my r11 is equal to 2, my r22 is equal to 1, and r33 is equal to 5. Okay, so this is what we got. And then our R matrix in this case is 2, 0, 0, 0, 1, 0, 0, 0, 5. Okay, this is the R matrix which we get. All right. Okay. So now this is the R matrix, and if you will cross multiply, you will again get this expression. Uh, so now we have to check whether is it positive definite or not. So let us say, is it positive definite? So how will we find if it is positive definite or not? Any suggestions? You can also, if your mm, mic is not working or something, you can also put in the chat any suggestions, right? Or any answers. You can try to be interactive. So now we have to find whether it is positive definite. So what we will do is we have to check these determinants. One is this determinant. Then we will go to the next determinant of this, and then finally the entire determinant. Okay. So we know that 2 is positive. So this is the first determinant. Okay, then we will check 2001. So this comes out to be 2. Similarly, we will check 200010005. This comes out to be 10. Okay, so this also is positive. So all these three things, all these three parts are positive. So that's why we can say that our expression, the quadratic expression, 2x1 square plus x2 square plus 5x3 square is positive definite. Okay, we can say it is positive definite. So this is the test. So this is a test to check for positive definiteness. Okay, so I hope there are no doubts till this. If there are any doubts, you can comment, you can ask questions. Please feel free. Also, you can stop me in between. Okay, so let us go to the next part. Okay, we have to find its definiteness. We found out. Right, let us go to the next question. What is the simple closed surface for the function v of x equal to 9x1 square plus x2 square? Okay, so mm, this question number 4. So v of x is equal to 9x1 square plus x2 square. Okay, so we know that this is positive definite. Okay, they're saying that v of x is equal to 1. So v of x is equal to 1. So this case A or surface A. Let us say this is surface A. Hmm. So it is 9x1 square plus x2 square is equal to 1. So how will this look? We have to write it in the form in which we can write the expression. So this actually is x1 square into 1 by 3 square plus x2 square upon 1 square is equal to 1. So that actually is like if you draw it over here, this is a x1, this is x2, right? So x2 will be 1 and x1 will be 1 by 3 minus 1 by 3 minus 1. So it will look like this. So this is surface A where v of x equal to 1. So in this surface, we can say v of x is equal to 1. Now let us go to B part, that is v of x is equal to 9. Okay, this is surface B. So how do we write it as? So we have 9x1 square plus x2 square is equal to 9. So we have x1 square plus x2 square upon 9 is equal to 1. So we have x1 square plus x2 square by 3 square and we have 1 square is equal to 1. Right? So I made a mistake. Like I have not drawn, considered it properly. So let me just rub out some parts. Let me just extend this line. Okay. So this, let us assume it goes till here. This also, let us assume it goes till here. And this is our minus 3 point. This is our minus 3 point, right? And this is our x1 1 point. This is our x1 1 point. Okay. So now this ellipse, which goes from minus, oh sorry, this will be plus 3. Okay. And this will be minus 1. So this ellipse, which goes like this, and like this. Okay. So this is the surface B. Okay, so this is surface B, and the overall objective of this question was for you to visualize and see that the surface A lies completely within the surface B. Okay, so the conclusion is that the surface A lies within the surface B. All right, it is completely inside, and so what it means that this v of x is equal to 1 is surface A, and v of x is equal to 9, right? So when v of x is less than something, it will be within that surface. So if you have v of x is equal to zero point 0.9, it will be like the smaller one. It will be something smaller. Okay. So those are within this bigger surface. Okay. So this is useful like when you will be considering stuff regarding Lyapunov stability. So are there any queries till this point? Okay. So the audience is understanding very well, I think. Great. So next we will check about stability, right? What is stability? Uh, so the next part is stability. So there are various ways which we can find stability. One is like a bounded input, bounded output method, which we can check whether the system is stable. Second is via the impulse response. So what is the property of the impulse response is it can give you the information of the system. That from the impulse response, you can find what is the step response, what is the ramp response, what is the response to the sine wave, cosine wave, like how the system will respond to any input. You can find out, you can determine that considering the impulse response. Because if you know the impulse response of a system, you can characterize the system, right? Although it is difficult in practical reality to get the actual impulse response, etc. Hmm. But that is a mathematical definition, and this is the powers of the impulse response. So if you have the impulse response of a system, you have that expression, and if you can integrate that from over the entire time duration till infinity, you can say whether the system is stable or unstable. Okay, so that is impulse response. Bounded input, bounded input. You give a bounded input, your output also has to be bounded. Okay, so stability means that it should not just grow to a very large value. It should be within certain limits. It should be confined to a certain region. So that is that's what stability means. Next is Lyapunov stability. Okay. Next is Lyapunov stability. So this is useful for nonlinear systems, and it can be used as well for linear systems as well. This theory can be used for nonlinear systems as well as linear systems as well. And it is based on the concept of energy. Okay, so Lyapunov had proposed this method and where he generalized energy function, and he used that energy function to determine if a system is stable or not, right? So based on that, okay, so let us go this point, lecture 17. Okay. I hope you guys have these notes, right? Where Sir has defined what is stability, right? And he's considered what is the sense of Lyapunov. Hmm. Okay. So this is one thing. One diagram is there, right? So there is a ball S of R. Okay, S of R is a ball. It is like the sphere. So I had shown this diagram. If you would remember, this diagram is there. So this is considering two dimensions. That is, I have x1 and I have x2. But when it becomes like n-dimensional or multi-dimensional, etc., they consider a sphere. Okay, they consider a sphere as shown over here. So there is a sphere, this S of R, and S of small r, and there's a sphere S of capital R, right? So now, sorry. So now, what is this point? If I can draw, okay, it's color green. What is this point? What is this point? So this point is like the initial condition. It is like the initial condition. So the system is going, so for one case, for one system, it is going out like this. It is going here, it is going here, it is coming here, then it is coming back here. Okay, so this is one case. This is one case, right? It is starting from here, it is going and coming back here. So the trajectory of the system, that is like how the system is moving, it is started from a initial condition within this ball S of R, but it is remaining within this capital S of R. Then we say that this system is stable. Okay, then we say that the system is stable. Next is we have another case where it starts from here and it goes here. And suppose it remains here, it stops over here, right? It has started within S of R, it has gone out of S of R, means it has gone out of S small r, but it is within S of capital R. So then also we say that the system is stable. Okay, it is not growing unbounded. Okay, it is not growing unbounded. Let us consider the third case. Some other color. Okay. In this case, it starts again from here, it goes here, and then it has started within S of small r, it has gone out of S of small r, but it is within S of capital R, and then it comes back into S of small r and it reaches the origin. It reaches the origin. Okay, that means that this is, and it stays there. So that means it is asymptotically stable. That means this system is asymptotically stable. All right. Means it has started from some initial condition, and then it is converging to the equilibrium point, okay, which is the origin in this case. So the system is asymptotically stable. In another case, it has, let us say, in this case, okay, it has started from here, it goes here, it goes out of S of small r, which all the other systems also went out of S of small r, but then it goes out of S capital R. Then we say that the system is unstable because it is growing, like the value of the state is increasing, it is just growing. So it is like kind of unstable, right? Okay. So any questions in this part till now? Okay, so there are four trajectories which are shown, and we commented whether it is stable, it is asymptotically stable, or whether it is unstable, right? Then there is something known as globally asymptotically stable. If this S of R was actually infinite, that is, it covered the entire state space. Okay, then we can say that is globally, then we are defining the stability in terms of the global, as a global form, right? So then we can say whether it is globally stable, it is globally asymptotically stable, or it is unstable, right? So that is also possible. Hmm. So this is the thing regarding stability. Okay, yeah. If SFR includes the entire state space, the definition apply in a global sense, right? So a linear system is if it is stable, it is asymptotically stable. And yeah, it is a generalization of the energy concepts, which you guys know. So how do we find out? Okay. So what it says is, I have a nonlinear system. So what is an example of a nonlinear system? Let us say what is a non-linear system. Simple system. We let us say x dot. We'll consider scalar system where x belongs to R1. Okay, that means x has only one dimension. So let us say x dot is equal to x square, right? So this is a non-linear system because it is raised to the power 2. So it is no more linear, it is non-linear, right? So what does it say? If that x is a real scalar function v of x continuous with continuous first order partial derivatives, such that v of x is positive definite, that is v of 0 is 0, and v of x is greater than 0 for x not equal to 0, and the derivative of v of x is less than 0 for x not equal to 0. Okay, so that we will consider. Okay, so let us do a simple thing. Let us say x dot is equal to minus x square. X dot is equal to minus x square. This is our system, right? And our this v of x, let us write it as x square. Okay, make it more easier and better to understand. Let us v of x square. This let us say minus 10x square. So my x dot is equal to minus 10x square is my system, and v of x equal to x square is my Lyapunov function. Okay, why it is my Lyapunov function? Because it is positive definite. It is positive definite, so a simple one I'm choosing. So v of 0 is equal to 0, and the rest of the time v of x is greater than 0. So now let us find a derivative, v dot of x. That is what 2x into x dot. Okay, so this is equal to 2x into minus 10x square. So this is minus 20x cube. Okay, so this is minus 20x cube. So what can we say about this? Now our v dot x is minus 20x cube. So they are saying that v dot of x should be less than or equal to 0. V dot of x has to be less than or equal to 0. Will it? So we first say v dot of 0 is equal to 0. Now if x is greater than 0, then v dot of x is less than 0. But if x is less than 0, then v dot of x turns out to be greater than 0. Okay, so in this case, this system is not stable. This system is not stable, right? So that is how we find stability in terms of Lyapunov function. Okay. Hmm. So let us try another thing. Let us try x dot is equal to minus 10x cube. Okay, v of x remains the same. V of x is equal to x squared. So now v dot of x in this case will be minus 20x squared into x dot, right? So that will again come out to be minus 20x squared into minus 10x cube. So that comes out to be 200x raised to 5. Okay. So again, in this case, it comes out to be unstable. All right. So this is the challenge. So this is the challenge with Lyapunov stability is we need to find a suitable Lyapunov function to determine stability. And that is not easy. Okay, that is very difficult to do. Okay. So Brenda, actually this class will end, like this meeting will end in kind of like in 6 minutes. So then I will again restart this meeting, okay? Because I'm not having the paid version of Zoom, I have the free version of Zoom. So there's a limit of 40 minutes. So once 40 minutes is over, this meeting will end automatically. And then immediately I will start the meeting again. So you'll have to rejoin in the same link. All right. Okay. So let us go to my question. Okay. This is the stability of linear systems, everything. All right. So there the problems we have to find this v of x, which is very difficult to find this v of x. Here, sir has given a question, and he has also given the Lyapunov function. And then they found the derivative, and then they found for which range of k it is stable. Right? They found out for which range of k it is stable. So let us go to our questions. Let us see what is the stability of the system in BIBO sense. Okay, let us consider this is our linear time invariant system. Okay, I think this is which question? Question 5. What is it given as? X dot is equal to minus 3, 0, 5, 3x plus 30u, and y is equal to 5 2x plus 10u. 5 2x plus 10u. So this is your A matrix is minus 3 0 5 3. B matrix is 3 0. C matrix is 5 2, and D matrix is 10. Okay. So can you tell me like which matrix is considered, you consider it for determining the stability? Like which matrix are we considering? Sorry? Yeah, the system matrix. So there is this matrix A, right? So like one method sir has told is we can find this A transpose R plus RA should be equal to minus Q. Okay, so this is one way. If we are actually using Lyapunov method, we have to use this method that we have to take A transpose R plus RA should be equal to minus Q, right? So we will, what is done in this method is we assume some positive definite matrix. We assume, okay, we will say some, let us say Q is 2 0 0 2. It is a positive definite matrix. That yes, delta.
Sir, how in what assumptions we assume Q? Is there any thumb rule or something like that to assume Q?
Assumption of what?
By what means we assume Q matrix?
This Q matrix. Okay. So the Q matrix, it has to be positive definite. That is the assumption. Like that we have to consider. Okay, and you usually you consider it such a way such that it is not difficult. Like if it is 1.25 some number, it is difficult, right? That's why we consider. Also, you might have Q matrix to be 2 1 1 2. This also is positive definite, but it is difficult in the mathematical way, right? It becomes more complicated. So if you use this Q matrix, it becomes easy. Okay. So we can use this method. We can then find some A transpose R plus R A, this to be equal to minus Q, where we consider R to be some R11, R12. This will be R12. This will be R22. Okay, and then you can do this entire thing, and then you can check whether this R matrix also should come to be positive definite. Okay, this also should come out to be positive definite. But this is a very mathematical, like it's mathematically intensive. Okay, so you have this is a linear system. We also know how to find the stability of a linear system. what we will do is we'll find the eigenvalues. We will do lambda I minus A, right? So it is lambda 0, 0, lambda minus A is what? Minus 3053. Minus 3053. So that will be lambda minus 3, 0, minus 5, lambda plus 3. So we have to find the determinant of this. Okay. Okay, so we have to find the eigenvalues. So this is the thing we do. We find lambda I minus A, the determinant of it we equate to 0. So that comes out to be lambda minus 3 into lambda plus 3 minus 0 is equal to 0. So we will get lambda minus 3 into lambda plus 3 is equal to 0. So our lambda is equal to 3 comma minus 3. So based on these eigenvalues, what can you say about the stability? Is this system stable or unstable? Okay, so it is unstable, right? Yeah. So that's why the system is unstable. Okay, so the system is unstable. So this is a easier method. Like I feel like this is easy. You just find the eigenvalues of the A matrix and you can comment regarding the stability of the system. You don't need to find this A transpose R plus R equal to minus Q, do all this multiplication, everything. It is like big hassle, right? It is a linear system. There are very well standard techniques to find the stability of this linear system. You can use that, right? Okay. One more point I'd like to point out is this is a, if you will see, this is a, there's a diagonal part is there, and this is zero. Okay, this is zero. So if you know that either the upper half or the lower half of your matrix is zero, then the eigenvalues are just these values. Okay, the diagonal elements alone are your eigenvalues, right? So that way you can easily tell whether the system is stable or unstable. And this is not like your normal, I don't know what you're studying right now, but it is not like your BTech or master's exams where you have to solve it and you get marks for your steps, everything. Here in the exam, it is either MCQ or it is either you have to write the numeric answer value, right? So there are some easy ways where you can see whether it is stable or unstable, it is asymptotically stable, marginally stable, etc. You can find out. Okay. So coming to stability, right? So here the system is unstable. We can say that the system is unstable. Suppose my lambda uh, came out to be, it came out to be minus 3 and minus 4. Then we can easily see, right, that the system is stable because both the eigenvalues are in the left half. Suppose we say our eigenvalues comes out to be, they are complex conjugates. It comes out to A plus or minus Bj. Okay, it is A plus or minus Bj. This is where it is fun, right? So now, when will the system be stable? Does the stability depend on A or on B? What does the stability depend on?
The part is in the left half of the screen, the system is stable.
Okay, so you are saying that if the lambda should be in the left half of the spin.
Depends on A.
Okay, it depends on A. So if it is in left half, that means your A will be less than 0, right?
Negative.
Yeah, the negative. So then we say that the system is stable. Okay, if your A is greater than 0, that is the right half, then we say that the system is unstable, right?
Yes.
Okay. What do we say when A is equal to 0? What happens then? Because if you remember that this is your x-axis, this is your s-plane, okay? Poles or eigenvalues we can consider. So it is in this part, it is in this line, right? Because the real part is 0. So it could be like this is plus bj, this is minus bj. So in this case, whether it is stable or unstable.
Is it marginally stable?
Yeah. So in this case, it is marginally stable. Okay. So this is so what I want you to keep in mind is you have a linear system. They've asked you to find the stability. Okay. So linear system stability is global. Okay. So this is also something which you must remember. So linear system stability is global. Okay. It's a global form of stability. That is, it is globally stable or globally unstable. Okay. So if A is less than zero, we can say for sure that the system is globally stable. If A is greater than zero, we can say that it is globally unstable. But if A equal to zero, it is a very like conflicting situation. Okay, like it is just on the verge of instability. So you cannot use the term global in that case. I feel okay. I'm not sure, but you can say that it is marginally stable, right? And in your assignments and in your MCQs, they ask like, is it BIBO stable? They asked, is it asymptotically stable, right? Or is it globally stable? That you must understand. If it's a linear system, you can make a comment in terms of the global sense, right? Okay, so these are some things with this question. Let me go to the next question. Oh, okay. Let me do this one first. So this would be which question number? Question 6. So, question 6. What is the system is x1 dot is equal to x1 plus x2 square. X1 dot is equal to x1 plus x2 square plus x2 into x3. X2 dot is equal to x1 plus x2. X1 plus x2 plus x1 square. And x3 dot is equal to x1 plus x3, x1 plus x3 plus x1 into x2. So is this system linear or non-linear?
Non-linear system.
Okay, it is a non-linear system because there are terms where the states are multiplied or states to the power of square. So what is done in this case is you acha. Also, is this system autonomous or non-autonomous system? Okay, I know autonomous is like a very advanced term probably. Like there are colleges now where we say that it is a autonomous colleges or it is a non-autonomous college, right? We like a autonomous college means it functions independently. It doesn't require any external influence. Like it is not governed by some board, right? Like we say that this college is comes under the Tamil Nadu State Board or Maharashtra State Board or something like that. But autonomous college is like independent. It is a college which is recognized and it is an autonomous institution. So it forms its own rules and it works according to its own rules, right? So this system is an autonomous system because there is no external input. Okay, in all these cases, it is 0 into u. Okay, it is 0 into u, right? So there's no effect of any external input, right? So this is one point. Now we have to decompose this system into a linear part and a non-linear part. So it has three states. It has three states where x is equal to x1, x2, x3, right? So let me write it down as x dot. My x dot is actually what? It's a matrix x consider x1, x2, x3 plus the nonlinear parts. So this is what's the nonlinear part? X2 square plus x2 into x3. Then it is x1 square, and this is x1 into x2. Okay, this is a nonlinear part. But the linear part is this x1, so 1, 0, 0. Then x1 plus x2, so 1, 1, 0. Then x1 plus x3, so 1, 0, 1. So this is the part. So this is the kind of like a matrix which we consider, and this is the g of x. Okay. So if you remember, sir had told that the nonlinear system has been written as a of x plus g of x. So into a linear part and a non-linear part, right? Okay. So any questions in this till now?
No, sir.
Okay. So then comment on the stability of the nonlinear system. Hmm. Okay. What is the equilibrium point of this system? What is the equilibrium point? And how do you find the equilibrium point?
X1 dot equal to x1.
Hmm. No, that's not the way. Like equilibrium point means you have attained the state of rest. Like you have come to a final point where you will not change. Okay, where there is no more change. Like what happens is uh, equilibrium rarely happens in normal scenario, but like let us say for a room, okay, you bring a coffee, hot coffee is there, you put it in a room, slowly it will cool down, right? Because its temperature is lot and the external temperature is less. So it will cool down such that it comes to room temperature. Then we say that it has reached thermal equilibrium. That is, it has reached steady state. So once it has reached steady state, what happens? The temperature of the coffee will not change. Will not change anymore. So when you consider that in the case of a dynamic system, which is like these are systems, right? We are considering the state space representation of a system and their dynamics. So their dynamics is dependent on the derivative. What is the derivative? It's like the rate of change. Rate of change. So at equilibrium point, there is no more change. So if there's no more change, what does it mean? That your x1 dot should be equal to 0, your x2 dot should be equal to 0, and your x3 dot should be equal to 0. So this is your equilibrium point where there's no more change in the states, that the change in the states is 0. So if our x1 dot is equal to 0, if x2 dot is equal to 0, and if x3 dot is equal to 0, what values of x1, x2, x3 will result in such a situation? I know it's three equations, but what do you think will be the values? Okay, so if x1 dot is equal to 0, x2 dot is equal to 0, and x3 dot should be equal to 0, that would happen in the case when x1 is 0, x2 is 0, x3 is 0. When everything is 0, you will get that result. Okay, you will get that result. Also, this is another thing I'd like to point out, that this is a non-linear system. So because it is a non-linear system, there can be multiple equilibrium points. It is possible that there can be multiple equilibrium points, but that you'll have to check very carefully. Okay, for now, we will consider that we have found one equilibrium point, that is the origin, and the other equilibrium points, we are not worried about them right now. We are worried about this one. We are worried about this case, equilibrium point around the origin, and we are finding the stability around the origin. Like in the neighborhood of the origin, we are trying to find the stability. Okay. So what do we know? We have found the A matrix of this, right? So now we have to find the stability. Oh, sure. Sorry. Like, how should we proceed now? What should we do? So the thing is, linear systems are very nice. Okay, you can find the stability and all that. And when we come to a non-linear system, we find it to be very, very difficult, so complicated, and we miss our linear systems. So what they sir has told is, you have a non-linear system, you decompose it into a linear part and a non-linear part. Okay, and you try to find the stability of the linear part. Okay, from that, if the linear part is stable, then you can say that it is stable, kind of stable around that operating point. If it is linear system is itself unstable, you can say that that equilibrium point, it is unstable, right? So instead of analyzing this complicated nonlinear part, we will just analyze the stability of the linear part. Okay, and we will check whether it is stable or unstable. If it is stable, we are happy. If it is unstable, we can't do anything. Okay, it is unstable. Okay, so now this is our A matrix. So can you find out the eigenvalues of this A matrix? So what are its eigenvalues?
Sir, I have a doubt.
Did it?
So for this non-linear system, we are separating
Mm-hmm.
into the linear and non-linear part. So we have to
Mm-hmm.
find the stability of the linear part. And if
Mm-hmm.
it is stable, then we say the entire system is stable. Do we say
There,
that?
no, yes, yes. This is the tricky part. Okay, if it is stable, we say that it is stable around the neighborhood. It is stable around a small part around the equilibrium point. We don't say that the entire place it is stable. Okay. For that,
Okay,
we have to find the Lyapunov function and do all those methods. That is complicated. Okay.
okay,
So this
okay.
is this is like a small test. Like if you are concerned about the stability around a small neighborhood around your equilibrium or operating point, you can linearize it and check the stability of the linear part. Right. That will tell whether it
Okay,
is stable or not unstable. Not stable. Hmm.
okay, okay, okay.
Okay. Okay. So were you able to find the eigenvalues of this A matrix?
Uh, this is the triangular matrix, so it's
Eh,
one.
Okay. So your eigenvalues are actually 1, 1, 1. Okay. So is this system stable?
No.
So it is unstable. Right? Okay. So it is unstable. Yeah. So are you a student or uh, faculty or like what? Or you're a PhD student, a PhD scholar? Or...
I'm a PhD student with that firm.
Okay. Studying in which college?
Anna Institute.
Oh, Anna University. Acha. My dad actually studied in Anna University and everything. So yeah. Hmm. Okay. So like, what is your course like? What is your field of study and research?
Power system.
Okay, power systems. All right. Then yeah. Okay, power system which will have to do a lot with matrices and everything, but all those things, right? Yeah.
Yes, this is a part of the course.
Uh, so, but then why were you assigned this course to go through? Like you have to do it for your credits or what?
Yeah, for credits.
Okay.
And
So,
my all stability aspects also, I chose this course.
okay, okay. Acha. So you have chosen only this course or you have to do even other NPTEL courses as well?
One more NPTEL course I have taken, and then two courses which are offered in
Oh, okay,
that I
okay.
have
Acha. Oh. And you have to do this within your first year or like what is the way?
within 2 years.
Okay, within 2 years. So you have to do 4 courses within 2 years.
Yes,
Okay. Okay. So you have already registered for the exam, right?
yes, I have that.
Uh-huh. Yeah, that's important. Yeah. Yeah. And yeah, this course is a bit difficult. I'll admit it is quite difficult. Mm. So even I find it difficult, everything. So I have done my master's in control systems. So this is something which I should know very well. But it I have to brush up, I have to revise, and it is not an easy thing. Like earlier and all, I used to teach. I taught like network analysis course or measurement course, which are like simple you undergrad stuff. So they were much easier. But this is a bit difficult, and
Yes.
uh, this course is not. Uh-huh.
Uh, we need to spend more time and it involves all basic concepts.
Hmm. Yeah, that's the thing. It involves lots of concepts and like differentiation, integration, and matrices. It's like positive definite, all these things. Yeah. So it's quite complicated. Also, many of the previous NPTEL courses like which I've done, like I'll have my job will be to solve the previous year assignment questions. So I'll just teach some theory and I will solve those questions and that's how the session goes. But in this case, I have to make my own questions and I have to solve it. So that makes it a bit more complicated. Like that.
Yes.
Yeah. Okay. Anyway, I'm trying. Like you could also have some feedback, like what I could improve or what things can be beneficial or useful. You could also share that way. Okay, and one more thing, like these videos are being recorded and they'll be uploaded on YouTube. So you have the links, right? You
Yes, I
get
have
those.
seen the previous videos through the
Okay,
YouTube
okay, okay.
links.
Yeah, correct, correct. Yeah. Okay, good, good. Okay, so we'll proceed. That we found the stability. Now let's go to the next question. Or let us consider the both stability of this discrete time system. Hmm. Okay. So, so which question number? Question 7. So we have to find the BIBO stability for discrete time system. Okay, so most till now what we were seeing, like x1 dot is equal to x1, right? Those are like continuous time. If we see this x1 dot is equal to x1, this is a continuous time system because it involves derivative, right? But when you come to discrete time system, we will write that x of k is equal to minus 2 of x of k minus 1, something like that, right? It it is written in terms of difference equations. Okay. So can you give an example of a discrete time system which you know? Like any example of a discrete time system, or whether it is just fictitious? Okay. So nowadays what's happening is we are like the world is becoming digital. We have mobiles, we have computers, then we have many digital controllers. Okay, like we have these things known as microcontrollers. You have what is known as a FPGA and various other things are there, right? So they work in digital domain and they take what is known as samples. Okay, they use a process known as sampling. So they take the nth sample, right? Then you consider for the n plus one sample, etc. Okay, so it is in terms of samples, right? It is discrete. It is in discrete time instance. It is not like a continuous. Like it's not like you take sample at 0 second, then you take sample at first after 1 second, the second, like that you do. Okay, you don't take so all the information between 0 and 1, though that between like 0.2 second, what has happened, 0.3 second, all that will not be there. You will not know. Okay, because it has we are only having the sample information, right? Let us say like if you have some waveform like this, right? You take the sample here, this information you have. You take the sample here, this information you have. You take the sample here, this information you have. But all this information, like all this information, you don't have. You lose it, right? So there are ways they use like interpolation and other stuff, complicated stuff are there. But just I want to say that there is something known as a discrete time system, and it is practically relevant, and it is like gaining lots of importance. Okay, so you would have studied digital signal processing, DSP course, etc. So one is we will consider the question is f of k is equal to a raised to k. So I have a discrete system which is given by f of k is equal to a raised to k for k greater than or equal to 0. So this is my impulse response. So this is the impulse response of my digital system, which I know. And now I want to find the stability of the system. Okay. So stability means what? I will have to find the summation of the impulse response, where k is going from 0 to infinity. So I have to find the summation k going from 0 to infinity a raised to k. So what will be this value? Also, one more thing is a is less than 1. Okay. So how will I find the summation of this? So if you will see, this actually is, if you put a k 0, a raised to 0 is 1. You put k as 1, it is 1. It is 1 plus a square plus a cube plus dot 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 dot. Okay. So what is this sequence known as? Any idea? What is this sequence known as? Okay, so this is actually a geometric progression. And its sum can be written as 1 upon 1 minus a, provided that a is less than 1. Right? Okay. So then can we say whether the system is stable or unstable? What can we comment about the stability? So if you will notice, it is 1 upon 1 minus a. A is less than 1. So even if a is 0, the value is 1. If a is zero point 0.1, the value will be some value greater than 1. But does this value become infinity? When will this value become infinity? When a is equal to 1. But we have told it forcibly that a is less than 1. Right? So this sum is always less than infinity. So this sum is always what you can say is finite. This sum is finite. Okay, so hence we can say that it is BIBO stable. It is BIBO stable. Right? Now let us consider the next case, where g of k is equal to k into a raised to k minus 1. System 2, g of k is equal to k into a raised to k minus 1. Right? So that means what? Let us say this is k, this is g of k. When k is 0, this is the value 0. When k is 1, it has the value 1 into a raised to 0, that is 1. It is 1. This is the value 2. It has 2 into a, it has the value 3. It has 3 into a square. It has the value 4. It is 4 into a cube. Right? So if so what we want is the summation of g of k, right? That is a summation k going from 0 to infinity, k into a raised to k minus 1. Right? That is what 0 plus a 0 sorry, plus 1 plus 2a plus 3a square plus 4a cube plus dot dot dot. Okay, then how do we find this sum? Right? This sum will be complicated. How do we find the sum of this? What is the method? So let us consider a simple geometric progression. We saw it, the geometric progression, where we have summation k going from 0 to infinity, a raised to k. This is equal to 1 upon 1 minus a. Okay, it is 1 upon 1 minus a. What we will do is we will differentiate with respect to a. Let us differentiate with respect to a. So that means what? We have d of dA summation k equal to 0 to infinity a raised to k. D of dA of 1 upon 1 minus a. Right? So if we look at the left hand side, summation comes out, summation k equal to 0 to infinity d of a raised to k upon dA is equal to d of dA 1 upon 1 minus a. Right? So this will be summation k equal to 0 to infinity. So what is this derivative of a raised to k? It comes out to k into a raised to k minus 1. This is equal to derivative of 1 upon 1 minus a is minus 1 into 1 upon 1 minus a square into minus 1, right? So that becomes summation k equal to 0 to infinity k into a raised to k minus 1 is equal to 1 upon 1 minus a square. Okay, it is 1 upon 1 minus a square, right? So we will look at what we have got earlier. We have to find the sum of k into a raised to k minus 1. Okay, we found that this sum is given by the expression 1 upon 1 minus a the whole square, right? Where a is less than 1. So this sum also is finite. And hence we can say that the system is BIBO stable. Okay. So any questions in this? Brenda, any questions? Brenda, sorry. Okay. So I have come to the end of the questions which I have prepared. So if you have any doubts regarding any particular topic, you can ask.
Have any doubts?
You don't have any doubts? Go ahead.
No. As of
Okay,
now,
okay.
I don't have any. I'm yet to solve that.
Okay, okay. Yeah, yeah, yeah. The assignment you have to submit it by Wednesday.
Yes, yes.
Mm. Yeah.
I've just completed watching the video lecture today only.
Yeah. Maybe this week was less only, 3 videos only, so it wasn't too long, but it's very conceptual. Very well. Yeah.
So I'm yet to start reading on this topic.
You have to start working on this topic.
Working on
Hmm.
that.
Yeah, yeah, yeah. It's true. Hmm. Let us consider a topic. Say, question 8. Let us say we have x dot is equal to minus a x, where a is greater than 0. Okay. It is just x belongs to R1. So that is just a scalar system. It's not a vector system. So now we have to find the stability. Okay, we have to find the stability. All right. So now this is dx of dt is equal to minus a into x. Okay, so we draw what is known as a line. This graph, we have x over here and dx of dt over here. Right. So this would be a line passing through the origin. Since it is So this is dx of dt is equal to minus ax, right? So y equal to mx plus c. So this will be a line like this. Okay, with the slope of a. Okay, so this is our line. So, like, I want you to think in terms of physically, like, what is the insight which you will get if you look at this. So, this is like, I forgot a term for this. Uh, like, I had studied this in nonlinear control. But if you look at this, you have x and dx of dt, right? So, now, suppose my x, draw, my x is over here, right? My x, let us say my x was at 1, right? Now my x tries to go to 2. Okay, x is trying to go to 2. That means I am going in this direction. That means my x is going away from the origin. Okay, the x is going away from the origin, right? Okay, so before that, I have to say here your origin or 0 is the equilibrium point. Okay, now my x is going away from the origin. It's going from 1, it is going to 2. What happens to my derivative? My dx of dt will become what? It will become minus 2x. Sorry, it will become minus 2a, and a is greater than 0, right? So, what does this say? As my x is trying to increase, the derivative, as my x is trying to increase, my derivative is becoming negative. So, if my derivative is becoming negative, what it means is, like as the x is trying to go away from the origin, since the derivative is negative, it will bring it back to the origin. It will bring it back to the origin. So that way we can say that the system is stable. That means if my x is greater than 0, then my derivative is less than 0. So if my x is trying to go away from the origin, my derivative will say that no, x should not increase, it should reduce. It is bring it back to the origin. Okay, that way we can say the system is stable. So this is we have considered for this region. Okay, for this region. Let us this entire region when x is greater than 0. Let us consider case when x is less than 0. When x is less than 0, what happens is my dx by dt will be become equal to, let us consider case x equal to minus 2. Then dx of dt will be equal to what? 2a. What does it mean? That my x is trying to go negative. It is not seen at all. X is trying to go negative. It's trying to go negative. Okay, it is trying to go kind of like that. But because my dx of dt is positive, it will increase x. X is trying to reduce, but it will increase x. So that's why it will bring it back. That way it will bring it back to the origin. That is why the origin is stable. Okay, that is why for this case, the origin is stable. Right? That is consider case when dx of dt, this is equal to ax. Again, ax greater than 0, but instead here there's no negative sign. So if my x is greater than 0, my derivative also is greater than 0. What does it mean? That if my x is increasing, the derivative says that x must increase even further. Okay, so there will be what will happen? There will be a further increase. Let us say my x is less than 0. That is, my x is reducing. The derivative will now be will be less than 0. That means it will further decrease. So what does this mean? Is that there's a divergence. from the origin. That means the equilibrium point, the origin, which is the equilibrium point under study, is unstable. Okay, it is unstable. Hmm? Okay. So any queries in this?
No, sir.
Okay. So let us consider case when x dot is equal to x square, right? So in this case, what happens? When x becomes greater than 0, the derivative again becomes greater than 0. When x becomes less than 0, the derivative is still positive. So what it means is, if this is x, this is your dx by dt, and you will plot it like this. This is your dx by dt, right? That means when x tries to become, next tries to go away, your derivative will bring it back. Okay, it will come back. It will come back to the origin. But when x increases from here, when x becomes greater than 0, the derivative will further increase it and it will go away. It will diverge. So when x is in this part, it is stable. In this part, it is unstable. Right? So basically, we say it is unstable because both it is not always going to converge to your equilibrium point. Right? Mm. So let us let us see some conditions. Lecture 18. Dot. Mhm. Okay. Do you have any doubt from the previous week topics? Any doubt from that? You could ask that. We can look into that. You can try something else. Mm, we can try this. We can try A transpose R plus R equal to minus Q. Or whether this will come. Okay, how do we find the values of R? Let us check this one case, right? So Q is 2002 and A is minus 3053. So we have A transpose R plus RA is equal to minus Q. I think I can start a new page. A transpose R plus RA is equal to minus Q. Q I took it as 2002. A is, go to my question. A is minus 3053. minus 3053. A transpose will be minus 3503. So A transpose R plus R A is equal to minus 3503 R11 R12 R12 R22 plus R11 R12 R12 R22 into A minus 305 and 3. So this will be equal to minus 3 R11 and minus 3 R11. Sorry, minus 3 R11 plus 5 R12, and this will be uh, minus 3 R12 plus 5 R22, and this will be 3 R12 and 3 R22 plus minus 3 R11 plus 5 R12, and then 0 into R11 and 3 R12. So this will be 3 R12. This will be minus 3 R12 plus 5 R22, and this will be 3 R22. So when we add it, it will become minus 6 R11 plus 10 R12, and here will be 5 R22. Here again it will be 5 R22, and here it will be 6 R22. Okay, so this will be equal to our Q. So this will be 2002 is this. So there's a problem. It is not coming equal because we are getting two conflicting situations. We are getting R22 should be equal to 0 and R22 should be equal to 3. So this is not possible. Okay, so instead, let me do a summary of what was taught today. So first we did the mathematical preliminaries, where we have f of x equal to x squared, and we saw its value at the origin is 0. And we know f of x is not equal to 0 when x is not equal to 0. So that means f of x is greater than 0 when x is not equal to 0. So we were able to say that this is a positive definite function. Okay, it is positive definite. Similarly, for minus x raised to 4, we showed that it is a negative definite function. In this case, it is indefinite because f of x can be greater than 0, it can also be less than 0. Right? So we can do some plotting. So this is how x goes. Y equal to x raised to 2. Four. So figure 1, plot of x comma y. Run this section. So this is a plot of this is the plot of the function. This is a plot of function. So this is how x is varied from 0 to from minus 2 to 10 to 10. And you can see f of x is always negative. It is zoom in from 1 to -1 to 1. That will give us a good idea. Okay. So if you see within -1 to 1, f of x is always positive. Okay, from -1 to 1, f of x is positive. But if I increase the range from 10 -10 to 10, then it will look as though it is only negative, but actually there is a small region where it is positive as well. But it is not shown. Another way to, so let me show again from 1 to -1, -1 to 1. We can see it is positive, and also there are, you can see that it is like disjoint. How to do is I can increase the this way 0.001. I'm changing it. So in this case, when you will observe, it looks smooth. The curve will look smooth. Okay, so this is one way. I plotted it to check whether it is, whether it is positive, definite, or indefinite. So this is, in this case, it is indefinite. Okay, it is positive from -1 to 1 and negative elsewhere. So it is an indefinite function. Next, what have we considered? F of x equal to x cube. Okay. So the next part, x I will vary from -10, 10.01 to 10. Y equal to x dot raised to 3. So this is my x cube. Okay. So now let us say figure 2. I plot x comma y. Okay, let me run this section. Okay. So this is the plot. So it is symmetrical around 0 and it is positive value. So let's it is negative. When x is positive, it is positive, and x is negative, it is negative. Right? We can do also for minus of x is to 3, then it just get interchanged. And just gets interchanged like this. Okay, so this also is an indefinite function. Okay. Now let us say this these 2x1 square plus x2 and things we have shown. Like how do we say whether it's positive definite or indefinite or semi-definite, all that. How do we write it in terms of x transpose Rx? What are these surfaces? How do we plot these surfaces? Also have shown what is BIBO stability, what is the impulse response, what is Lyapunov stability. Lyapunov stability has two ways. You have a direct method in which you have your uh, you take a Lyapunov function and you do v of x, you find the derivative of that and see the conditions of it, and then you can come into the stability, but direct method is quite difficult. There's an indirect approach in which we have a nonlinear system. We linearize that nonlinear system. We decompose into a linear part and a nonlinear part, and then we check the stability of the linear part. Okay. And once we find the stability of the linear part, we can say whether it is stable or unstable in a small neighborhood around the operating point. Okay, if we already have a linear system, then we can just directly find the stability by using the simple method of finding the eigenvalues. And if the matrices have this upper triangular or lower triangular or diagonal matrix, then we can easily find what are the eigenvalues and we can easily comment about the stability. Right? Then also regarding the case when it is stable, unstable depending upon the its location in the left half plane or in the right half plane. Right? Then what are the various equilibrium points of a nonlinear system? And then we decompose it into a linear part and into a non-linear part. And then we find the stability of A. Since all the eigenvalues are 1, 1, 1, it is an unstable system. Then we consider a case for the BIBO stability of a discrete time system. Okay. So we have considered case f of k equal to a raised to k. Okay. And a is less than 1. If a is greater than 1, then it will be unstable. But if a is less than 1, then we consider the case where we do the summation. And what we are doing is we have to find the BIBO stability. So we are finding the sum of the we are finding out the sum of the impulse response. In continuous time, it will be the integration of the impulse response. But in discrete time, we find the sum of the impulse response. Okay. So that sum is found out. And since it's geometric progression, we can easily find out it to be 1 upon 1 minus a. Next, we consider a case where it is k into a raised to k minus 1. Now, how do we tackle this situation? What is done is this is g of k, right? We have the geometric progression formula a raised to k, which is equal to 1 upon 1 minus a. What do we do is we differentiate with respect to a, right? So this summation is here, both sides we differentiate, and then we take the sum outside, okay? Because sum is only dependent on k, it's not dependent on t. So we put a derivative inside. Then this becomes k into a raised to k minus 1, etc. And when we find a derivative of this, it becomes 1 upon 1 minus a square. So you get it in terms of summation k equal to 0 is k into a raised to k minus 1 is equal to 1 upon 1 minus a square. Okay, and the sum is 1 upon 1 minus a square. It is a finite number because a is less than 1. So finite. So we can say that the system is BIBO stable, right? Okay, then regarding depending on the derivative and the orientation, we can find whether it is stable or whether it is unstable, whether to further increase or further decrease, whether there's a divergence or there's a convergence to the origin. All right. Okay, so as Sir has also used an example and he has already has the Lyapunov function. What is instability? What is it to be stable, unstable, all these things, stability in the sense of Lyapunov. Like it is a more broader perspective to stability. It is not compressed form of stability. Okay. Over here, it is actually there's 0 to infinity g of t dt is infinite, is finite. Then we say that the system is stable, and this is the Laplace inverse of the g of s. Okay. Hmm. Okay, so there's a nonlinear system x dot is equal to f of x, and then we do the Taylor series expansion of it. In Taylor series expansion, what we are doing, the f of x, we are replacing by f of 0, plus it's the first order terms, then the second order terms, and then the higher order terms. So what happens is this f of 0, it is 0, because we consider that x is the equilibrium point, 0 is the equilibrium point, so at the equilibrium point, the derivative is 0. So f of 0 is 0. So f of x is actually given by this. Okay, so this is the linear part and this is the non-linear part, because it contains second order and higher order terms. So we are decomposing it into a linear part and a non-linear part. Then we have to find a positive semi-definite matrix Q, and we have to find it. If that is found, then we can say that the system is stable. All right. If v dot of x is less than 0 in a region around the origin, then we can say that x is a region around the origin in which the nonlinear system is stable. Okay. So they have considered this expression and they have solved it also. And how they got R, etc. They have found. Okay, so there are various things taught by Sir. How we had earlier last week touched upon controllability and observability. What is stability, right? And how what is in terms of Lyapunov stability and why it is used in various things. Okay, what is a scalar function? There's a range in which there's an interval of the scalar function, right? Negative, definite, negative, semi-definite, etc. What is a spherical region also was shown. And these are the cases when it is positive definite or it is negative definite, positive semi-definite or indefinite, etc. Okay. So quadratic forms are very important and it can be written in terms of x transpose Rx, right? And how we have to consider only the symmetric part. It should not, because any matrix can be written in terms of the symmetric and skew symmetric part. And we are only considered with the symmetric part. Okay, how do we find? Through Sylvester's theorem, this is how we find whether a quadratic form is positive definite or not. Okay, and another thing is definiteness of a quadratic form is global. It's throughout the state space. Okay, and we touched upon what is a closed surface and how we drew it and everything we showed. Okay, so thank you. I'll end this session.